All right, welcome everyone. Today we're going to do something really interesting. We're going to take one of the most important numbers in climate science and industry, the carbon footprint of steel, and we're going to tear it apart. We're going to build it back up from scratch using nothing but first principles. Think of it as a deep dive into the fundamental chemistry and physics to see where every single gram of carbon dioxide actually comes from in the steelmaking process. So here's our roadmap for today. First, we'll set the stage with what we call steel's carbon dilemma. Then we'll get right into the core chemistry, this thing called the reduction problem. After that, we'll roll up our sleeves and do the math, the stoichiometry, to figure out the emissions that are baked into the process. Then we'll layer on the massive energy cost, before finally, we add it all up. This whole process will show you, step by step, exactly why steel is known as a hard-to-abate sector. You know, it's hard to overstate how important steel is. It's literally the backbone of our modern world. Our buildings, our cars, our infrastructure, you name it. But, and this is a huge but, making it comes with a massive environmental price tag. The iron and steel industry is responsible for somewhere between 7 and 9% of all human-caused CO2 emissions globally. That is a gigantic slice of the pie, which makes figuring out how to clean it up absolutely critical. And here is the number at the very center of this whole discussion. On average, for every single ton of steel we create, we pump about 1.8 tons of carbon dioxide into the atmosphere. Just think about that for a second. The waste product by weight is almost double the actual product. It's a staggering figure, especially when you think about the millions upon millions of tons of steel we produce every year. So, this leads us to the big question for today's session. Where does this 1.8-ton number actually come from? It's not just some random estimate. It's a number that's dictated by the fundamental laws of chemistry and thermodynamics that have been at the heart of steelmaking for centuries. So let's start digging in and unpack the science behind it. Okay, so the first and probably the biggest piece of the puzzle comes from the basic chemistry of how you make iron. See, to get pure, usable iron, you first have to solve what metallurgists call the reduction problem. On planet Earth, you don't just find chunks of pure iron lying around. Over billions of years, it's reacted with the oxygen in our atmosphere. So what we dig out of the ground, iron ore, is really just iron oxide. The most common form is called hematite, or Fe2O3. You can basically think of it as iron that's completely and thoroughly rusted. So the very first job of a steelmaker is to reverse that process, to break those super strong bonds between the iron and oxygen atoms and set the pure iron free. And that process of yanking oxygen off of a compound, that's called chemical reduction. Now, to pull this off, you need something that wants to bond with oxygen even more than iron does. This is your reducing agent. You need something that will come in, steal the oxygen away, and leave the iron behind. And for hundreds of years, the cheapest, most effective reducing agent we've had is carbon, which we get from coal in a purified form called coke. And this right here is the fundamental chemical reaction that makes it all happen. Now, this is a simplified version. Inside a real blast furnace, it's a multi-stage process with carbon monoxide doing a lot of the work. This equation shows us the net result, which is what matters for our carbon accounting. On the left, you have your ingredients, iron oxide and carbon. The carbon goes in, does its job reducing the iron oxide. And on the right, you get your products. You get your pure liquid iron, that's what we want. But, and this is the critical part, you also get an unavoidable byproduct, carbon dioxide. The chemistry guarantees it. Okay, now it's time to translate that chemical equation into real-world numbers. We're going to use stoichiometry, which is just a fancy word for the math that lets us figure out the exact amounts of stuff we get from a chemical reaction. This is how we're going to calculate the absolute minimum amount of CO2 that has to be created to make a certain amount of iron. These are called process emissions because they are baked right into the chemistry itself. So, to do our math, we need a few key numbers. These are the molar masses of the things we're interested in. Just a quick refresher, molar mass is just the weight of 1 mole of a substance. So for our purposes, we'll use these values. Iron is about 55.8 grams per mole, carbon is 12.0, and carbon dioxide, that's 1 carbon plus 2 oxygens, comes out to 44.0 grams per mole. Our calculation is going to be a really straightforward 3-step process. First, we'll figure out the total mass of iron we get from one run of our chemical reaction. Second, we'll calculate how much CO2 is created right alongside it. And finally, we'll just figure out the ratio between the two. Simple as that. All right, let's dive into step 1, the mass of the iron. If we look back at our balanced equation, 2Fe2O3 plus 3C goes to 4Fe plus 3CO2.
You see that number 4 in front of the Fe? That coefficient tells us we produce 4 moles of pure iron. So to get the mass, we just multiply that by the molar mass of iron. So 4 moles times 55.8 grams per mole, and that gives us a total of 223.2 grams of iron.
Now for step 2, and this is the really crucial part, the CO2. The chemical equation locks the products into a fixed ratio. See the 3 in front of the CO2? That means for every 4 moles of iron we make, the reaction forces us to create exactly 3 moles of carbon dioxide. There's no way around it. So we do the math again. 3 moles of CO2 times its molar mass, 44.0 grams per mole, gives us 132.0 grams of carbon dioxide.
And now for the final step of our calculation. We just need to find the ratio. All we have to do is divide the mass of the CO2 we produced by the mass of the iron we produced. So that's 132.0 grams of CO2 divided by 223.2 grams of iron. This will give us the exact amount of process emissions per unit of iron.
And when you punch that into a calculator, you get a ratio of about 0.59. Since the units of grams cancel out, this ratio works at any scale, whether it's grams or tons. So what does this mean? It means that for every 1 ton of pure iron you make using carbon, the laws of chemistry dictate that you will produce at a bare minimum 0.59 tons of CO2. This is the absolute floor. You can't engineer your way around it. It's a fundamental consequence of the chemistry. But that's not the whole story, not even close. That 0.59 tons is just from the chemical reaction itself. The stoichiometry tells us what happens, but it doesn't tell us what it takes to make it happen. And what it takes is a mind-boggling amount of energy, mostly heat. This is the thermodynamic cost, and it's our second major source of emissions. To get this chemical reaction going and to actually melt the iron ore into a liquid, a blast furnace has to be kept incredibly hot. We're talking temperatures over 1,500 degrees Celsius in some parts. That is hotter than most lava flows. You need this intense heat to make the reactions happen quickly and to separate the molten iron from all the other rock and impurities, which form a layer of slag on top. Keeping a factory-sized oven that hot, 24/7, takes an unbelievable amount of energy. So, how do they generate all that heat? Well, primarily by burning more carbon. This is where the coke plays a second crucial role. Part of it is used as the reducing agent, like we just calculated, but a huge chunk of it is just burned as fuel to heat the furnace. And of course, burning carbon releases its own stream of CO2. On average, these energy emissions add about another 1.21 tons of CO2 for every ton of steel produced. Okay, so now we have our 2 main culprits. We have the emissions from the chemical process itself, the stoichiometric emissions, and we have the emissions from burning fuel for heat, the thermodynamic energy emissions. Now we can finally put them together and see if we get back to that number we started with. This chart really lays it out perfectly. On the left, you have our 0.59 tons of CO2 that are chemically unavoidable. But look at the bar on the right, the 1.21 tons from the energy needed to generate heat. What's so striking is that the emissions from just keeping the furnace hot are more than double the emissions from the core chemical reaction itself. The thermodynamic challenge is actually a bigger carbon problem than the chemical one.
So let's do the final addition. We take the 0.59 tons from the process emissions and add the 1.21 tons from the energy emissions. And what do we get? 1.80 tons of CO2 per ton of steel. And there you have it. We've deconstructed the number and built it back up from scratch, using nothing but chemistry and physics. And this whole journey we've just been on, from the chemistry to the math to the thermodynamics, this explains exactly why steel is the textbook example of a hard-to-abate industry. The CO2 isn't just coming from a smokestack you can slap a filter on. It's woven into the very fabric of how we've made steel for centuries. So what's the solution? Well, to truly decarbonize, you have to fundamentally change the chemistry. On the left is the old way, using carbon, which always gives you CO2. But on the right is the leading idea for the future, using hydrogen gas as the reducing agent instead. Look at that reaction. Iron oxide plus hydrogen gives you pure iron and H2O, water vapor. That's it. If there's no carbon in the recipe, you simply can't make carbon dioxide. But this isn't a simple swap. It requires a completely new type of technology and a total paradigm shift for the industry. And this brings us to the final and maybe the most massive question of all. We know the chemistry for green steel works, but to make all the green hydrogen we would need, which means splitting water using electrolysis powered by renewables, is a challenge on an almost unimaginable scale. We've solved the chemistry problem,
only to create an enormous energy problem. We would need to build out an amount of clean electricity and electrolysis capacity that just dwarfs what we have today. So the future of steel isn't just about steel anymore. It's completely tied to the future of our entire energy system. And figuring that out is the challenge we're facing right now.